Hello, this is a presentation on bolting fundamentals. This presentation covers the basics of what bolts, nuts, and washers and bolting assemblies are, which grades are available, and when washers should be used, when they aren't required. And it covers installation of fasteners, pre-installation verification, installation inspection, and storage of fasteners. There's a separate bolting presentation that covers failure modes associated with bolted joints and bolted connections. That's a presentation that I cover that I call bolted connection fundamentals instead of bolting fundamentals. So that would be a separate presentation. Let's get started. So the two primary methods for making connections in structural steel are bolting and welding. Shown on the left here is a worker installing some bolts, and then shown on the right is a worker making a weld, presumably in some sort of a column. Joints and connections that are made in a fabrication shop are called shop connections, whereas connections and joints that are made in the field by the erector are called field connections. Each fabricator and erector will have their own preferences to whether they prefer bolting or welding in the field or in the fabrication shops. But generally speaking, field connections are typically bolted and shop connections are often welded. Now that's not to say you can't do it the other way around. In fact, welding is sometimes used in the field where bolting is either impractical or undesirable, and sometimes fabricators will do bolting in the shop even if welding is easier in that location. And this shows a welder working in a fabrication shop on the left, and it shows a iron worker pre-tensioning a twist-off bolt or a tension control bolt on the right. Okay, as I said at the beginning, this presentation covers bolting, basically the installation of bolts and when and where washers are required and that sort of thing. Welding is covered in a separate presentation, and even failure modes associated with bolting are covered in a different presentation as well. Okay, we're going to refer to the AISC specification, Chapter J, where appropriate, but there's a different specification that governs bolts and bolted joints. That's the Research Council on Structural Connections. They have a specification on structural joints using ASTM A325 and A490 bolts. The last edition of it was the 2014 edition. It's included in your manual. There's a newer edition that is due to be released either in 2021 or 2022, and I'll make reference to that occasionally throughout this presentation. Bolting assemblies are composed of a bolt, one or more washers, and a nut. This slide illustrates some of the dimensions of bolting assemblies, including the overall length of the fastener, measured from the underside of the head to the end of the threads, the length of the shank or the body of the bolt, the length of the threads of the fastener, and the grip or the thickness of the material that's being joined by the bolt. And then, of course, the diameter of the fastener, which is measured through the body or through the shank of the bolt. Table 7-14 out of the AISC manual gives common dimensions for structural bolts, and these bolts are available in diameters of 1/2 inch through 1.5 inches in increments of 1/8 of an inch. They are available in lengths up to about 10 inches commonly. The length increments are 1/4 inch up to 5 inches, and in length increments of 1/2 inch above 5 inches. Anything above about 8 to 10 inches in length, you are going to have to special order. A325 bolts that have a length less than or equal to 4 times their diameter can be fully threaded, and the most common diameters are 3/4 inch, 7/8 inch, and 1 inch. The most common bolt used in structural engineering is a 3/4 inch diameter A325 fastener. If you look at the AISC specification, we have these 4 groups of bolts that are available. The first is an A307, commonly referred to as a low carbon steel bolt. It has a tensile strength F sub U of 60 KSI. This is not commonly used for joining or connecting primary members. This is more commonly used for secondary members or for non-structural work like connecting railings and things of that nature. We have group A bolts that have a strength of F sub U equal to 120 KSI. We have group B bolts that have a strength of 150 KSI, and then finally group C bolts that have a strength of 200 KSI. Group A bolts are composed of F3125, grade A325, or grade F1852 bolts. These are the most common bolts that are used in building construction. And Group B bolts are ASTM F3125, grade A490, or grade F2280. These are slightly less common. They're stronger, but they cost just a little bit more. The third group, Group C bolts, have a tensile strength of 200 KSI. They're relatively new to the construction industry in the U.S., and in theory they're available in larger diameters of an inch, inch and an eighth, and inch and a quarter, but currently they're not available in the United States. If you look at the RCSC specification, the grouping of the fasteners is a little bit different. We have Group 120 bolts instead of Group A bolts, but they're still composed of F3125, grade A325, and grade F1852. We have the Group 150 fasteners as well, again composed of ASTM F3125, grade A490, or grade F2280 bolts. But there's another grade of bolts included in RCSC. It's Group 144 bolts. These are ASTM F3148, grade 144. They have a unique spline drive on the end and allow for the combined method of installation. ASTM F3125 bolts are generally available in varieties that are shown here. The first two have a heavy hex head, and the third one is shown with a button head. Heavy hex means that the head of the fastener is a little bit thicker and larger than would be a typical hex head. A typical hex head would be a type of bolt that you could find if you went to Home Depot or Lowe's and looked up an ASME grade 8 bolt or grade 5 bolt. So the second and the third one are shown with a spline that is attached to the end of the bolt, and these are typically installed by using a special wrench that rotates the nut relative to that spline until the spline actually twists off through that annular groove that you can see there. So as such, the first bolt is referred to as a heavy hex style fastener, where you would use a hex wrench to rotate the nut relative to the head of the bolt. And the second and the third style are referred to as twist-off style bolts, where you'd use a special wrench to grab the spline and rotate the spline of the bolt relative to the nut. We also use the term tension control, or TC bolts, in place of twist-off, but twist-off is the official terminology. Okay, if you look at the ASTM F3125 specification, it comes with 6 different grades of fasteners. You have the grade A325, which is a hex variety, 120 KSI, and you have the F1852, which is the twist-off or tension control variety of the 120 KSI bolt. If you're looking at 150 KSI fasteners, then the A490 is the heavy hex, and the grade F2280 is the twist-off version. And then we have 2 metric grades that are included as well, a grade A325M that has tensile strength of 830 megapascals, and a grade A490M, which has a tensile strength of 1040 megapascals. Metric bolts aren't used very much in the United States at all, though. ASTM 3148 bolts, or the Group 144 bolts, are available as shown here. So they come either with a hex head or with a button head, sometimes referred to as a round head instead of a button head, and they all have a spline on them, though the spline is different than the twist-off bolts. These spline styles are fixed splines, and the method of installation is a combined method where you use torque and angle. So these are referred to as T and A 144, or torque and angle bolts, and 144 KSI strength. And the method of installation here is a combined method where you have a special wrench that grips the spline and turns the nut relative to the spline of the fastener, and it achieves a snug tight condition using a torque, and then achieves a fully tensioned condition by rotating the nut by an additional angle, thus the words or the moniker torque and angle. Okay, the F3148 fasteners are available as grade 144s for right now. I think that the inventor of these fasteners, Chad Larson, had envisioned possibly offering additional grades, but that hasn't come to fruition yet. The last bolts that we'll discuss here are ASTM F3111 and F3043 bolts. These are the 200 KSI bolts, and they feature a heavy hex variety that is the F3111 and a twist-off variety or a twist-off style that is the F3043. You might also notice that these bolts include a reduced shank that helps them achieve the higher strength without having issues with lack of ductility. Okay, these fasteners have a strength of 200 KSI, and ASTM F3111 refers to the heavy hex style, and F3043 refers to the twist-off style. However, these bolts aren't available in the United States as of right now anyways. All ASTM bolts are required to have their designation stamped on the head of the fasteners. So you can see that in the picture that's shown here. If you find a bolt on a job site that doesn't have the designation stamped on them, then they're not truly an A325 or an A490 or an F1852 bolt. They're probably some type of an imposter, or maybe they're a lower grade A307 fastener or something like that. So in addition to the ASTM designation that you can see stamped here, there's also the little delta sign, or the LE, and that indicates the manufacturer of the bolt. And the A325 shown here has 3 radial lines that also indicates the type of fastener. So the head markings are explained in the RCSC specification, so you can see the manufacturer mark there, indicated as XYZ in this figure. And if you see 3 radial lines, that's indicated as a Type 1 fastener. Type 3 fasteners have the designation underlined. You can see the underline for the A325, and Type 3 fasteners are weathering steel bolts. There used to be a Type 2 fastener some years ago, but the Type 2 was withdrawn from the ASTM specification, I think, in around the 1990s. Okay, in addition to the different types of fasteners, you can also look at different finishes that you have for the bolts. You can have a plain or galvanized. There are some other coatings as well, like a dacrymet coating and things of that nature. It's considered to be acceptable right now to galvanize A325s or F1852 bolts. I think it's going to be okay to galvanize Group 144 fasteners, but right now it's problematic to do galvanizing of A490s or F2280 bolts. There are 3 different types of joints that are defined in the 2 specifications. There are snug tightened joints, pretension joints, and slip critical joints. Snug tightened and pretension joints are defined more broadly as bearing type joints, and slip critical joints are defined more broadly as friction type joints. The 2 different types of joints, bearing and friction, are shown here at the bottom. If we zoom in a little bit, first on a bearing type joint, you can see that the load passes through the joint first by bearing contact between the connected material and the bolt, then through shear transfer across the shear plane of the fastener, and then again through bearing contact between the second plates and the bolt itself. In a friction type joint, however, the transfer of load occurs through friction between the connected plies, and the bolt is basically there to provide the normal force so that the friction forces can develop. Bearing type joints are defined more formally as a snug tightened or pretension joint with bolts that transfer shear loads and for which the design criteria are based upon the shear strength of the bolts and the bearing strength of the connected materials. Failure modes that one would consider for a bearing type joint include bolt tension or shear, bearing and tear out, block shear, tension, compression, or shear failures of the connecting elements, and similar types of failure modes. A snug tightened joint is a joint designed as a bearing joint in which the bolting assemblies have been installed to the snug tight condition. The slip resistance of a snug tightened joint is basically expected to be 0. A pretension joint is a joint designed as a bearing joint in which the bolting assemblies have been installed to the fully tensioned condition. However, the slip strength of the joint need not be greater than the factored required strength of the joint. In this case, the slip resistance of the joint is there basically as a serviceability issue for the joint or for the connection or for the structure. A slip critical joint is a joint that has been designed to transfer shear loads through friction. The slip strength of the joint must be greater than the factored required strength for the joint. Washers are part of bolting assemblies, and they're used basically to distribute the force or the stress from the bolt over a larger area of the base metal. They also help to reduce gouging of the softer base metal during the tightening process, and they're in place sometimes to cover an oversized or slotted hole. ASTM F436 are the default washers that are used. Those are the ones that are shown on the bottom left in this slide. And occasionally you'll see the use of tapered washers when you have sloping surfaces. For example, the flange of a channel or an S shape have a tapered thickness, and in order to provide a true bearing surface for the nut and the head of the bolt, you use a tapered washer. So basically, the bolt material is much stronger and much harder than the base material. And if you were to just take a nut or a bolt and tighten it directly against the softer A36 or A572 grade 50 base metal, you would end up gouging that material, and the material would end up galling the bolt, or the nut material would end up galling the base metal. So in order to prevent that, you put a hardened washer in between them. And the washers are a higher strength steel, but basically it's the hardness of the washer that is most important, because it prevents the bolting assembly or the components of the bolting assembly from digging into the base metal. So where and when washers are required can be a bit confusing, and you'll probably find some disparity between the RCSC specification and the AISC specification. In general, however, you want to put a washer under the turned element during the tightening process for a bolting assembly. So if the head is going to be held and the nut is going to be turned, you would want a washer under the nut. On the other hand, if the nut is going to be held but the head is going to be turned, then you would want a washer under the head of the assembly. More specifically, washers are required under both the head and the nut of A490 assemblies when you use those with a base metal that has a strength less than 40 KSI. On the other hand, if you're using a 2280 assembly, then you need a washer only under the nut. Remember, the A490 is a hex configuration, or a heavy hex style, and the F2280 is the tension control or twist off style bolts. Both of those are 150 KSI. Washers are required under the head and nut of all F3111 assemblies, and they're required under the nut only for F3043 assemblies. And remember, the F3111 and 3043 assemblies are 200 KSI bolts. The 3111 is the heavy hex style, and the F3043 is the twist-off style. Okay, washers are not required when you have snug tightened joints, unless there's sloping surfaces where you'd use a tapered washer, or unless there's an oversize or a long slotted hole. In that case, you need to provide a washer to cover the opening in the hole that might not be covered by the nut. And we also have washers that are often required in pretensioned or slip critical joints, depending on the method of pretensioning. All right, let's talk for just a minute about the erection of steel structures and the implications that it has on bolting. So during hoisting, connectors, and in this case I mean the people actually doing the connecting, connectors will install a minimum of 2 bolts per connection, and then the remaining bolts are installed and tensioned usually later on after the structure is plumbed. So basically you have a raising gang of the erection crew, and they'll come in with the crane and use that to set members, and they'll put at least 2 bolts in, and in theory they're required to put a washers and nuts on those bolts, and at least snug them up before they release the crane. And then they usually have a different bolting crew that comes in after the fact to put the bolts in, and then if pretensioning is required, to actually do that pretensioning. This is an interesting case. There have been several failures in the United States because connectors or the raising gang don't put in enough bolts during the erection process. In fact, there was a post office failure in Chicago where a beam fell from a building that was being constructed, and it was found out that the reason why was that the raising gang put 2 bolts in, but they didn't put nuts on some of those bolts, so that led to a failure. In another case here in Cincinnati, there was a failure during the construction of the casino downtown, and as I understand it, that failure resulted because they poured a concrete slab on top of a beam before the bolting crew came in and installed all of the bolts and the connections that were supporting the beam that were supporting the concrete slab. So they got the order of operations mixed up a little bit there, and it led to a failure. Okay, there's another provision in the OSHA guidelines that says that at no time shall there be more than 4 floors or 48 feet, whichever is less, of unfinished bolting or welding above the foundation or uppermost permanently secured floor, except where structural integrity is maintained as a result of the design. So basically, this is a provision that says that the raising gang can't get too far ahead of the bolting gang. So you can't go more than 4 stories above the part of the structure that has all of the bolts installed and pretensioned if pretensioning is required. So bolts on a typical steel job site are installed either to the snug tight condition or to the fully tensioned condition. Bolts are permitted to be installed only to snug tight when they're used in bearing type connections, or when you have group A bolts that are used in joints that are subjected to tension or combined shear and tension, where loosening or fatigue due to vibrations or load fluctuations are not a consideration. Okay, bolts to be tightened to a condition other than snug tight have to be clearly identified on the design drawings. So if nothing is called out on the design drawings, then it's assumed by the contractor that those bolts will only be snug tight. Okay, AISC 2016 says that the snug tight condition is defined in the RCSC specification. And then if we go to the RCSC specification, it says that the snug tight condition is the tightness that is attained with a few impacts of an impact wrench or the full effort of an iron worker using an ordinary spud wrench to bring the plies into firm contact. And it's interesting because the definition of snug tight is one of those things that seems to change every time there's a new issue or new release of the specifications. But this has generally been the case for quite a while. Basically, the full effort of an iron worker using an ordinary hand wrench or the few impacts of an impact wrench. The problem with this is, though, that not all iron workers are created equal. So defining the full effort of an iron worker with an ordinary wrench, in some cases you get a bit more effort from one iron worker than you might from another. Shown on the left here is a worker installing bolts using an impact wrench, though in this case it's an electric impact wrench and not a pneumatic or an air-driven impact wrench. And the electric impact wrenches tend to have a much lower torque capacity than the pneumatic wrenches. So if you're using an electric wrench like this one, it's probably going to be with a smaller bolt diameter where you don't need to have as much tension. On the right is an iron worker using an ordinary spud wrench, and you can see the wrench has a tapered handle. If you look at the worker's right hand, you can see that the handle of that wrench has a point on it, and that's used to align the holes of the joint before the bolts are put in. So you can use that as an alignment pin. And then actually you can see in the holster of the iron worker's tool belt right here, for example, that is a drift pin that is also used to align the joints before bolts are put in. Some of the tools that you would commonly see bolting crews using are shown on this page. On the slide on the left, you see a couple of different spud wrenches, 2 different sizes there, and then an alignment pin or a drift pin that's shown there as well. And then in the center image is a pneumatic impact wrench, and you can tell because it has a hose running to it instead of a cord. And then over on the right, you can see a couple of mobile air compressors that are used to drive the pneumatic tools. Bolts that are used in pretensioned or slip critical connections have to be tightened to a fully tensioned condition. AISC lists the required bolt pretension in table J3.1, and you can see that on this slide. So you have in the first column the bolt diameter going from half an inch up to an inch and a half, and then you have the three different groups of bolts. You have the 120 KSI bolts, group A, the 150 KSI group B bolts, and then the 200 KSI group C bolts. So the minimum pretension is basically 70% of the tensile strength of the bolts, but it's the tensile strength calculated using the effective area of the fastener and not the gross area of the fastener. So there's a little bit of magic in the calculations, if you will. RCSC also provides a table for the minimum pretensions. This table comes out of the 2022 edition of the specification. It's only available in draft right now. It's not hasn't been released yet. But you can see that they again list the minimum specified pretension as a function of the bolt diameter or the bolt size, and then they break it down into the group 120 and the group 150 bolts. Group 144 bolts, the torque and angle fasteners, have the same minimum specified pretension as the A490s or F2280s. RCSC doesn't include the F3111s or F3043s, the 200 KSI bolts. So in the end, for pretensioned and slip critical connections, we need to provide a minimum pretension in the fasteners. In order to do that, we need to use one of the methods that is included in the RCSC specification. AISC just provides a reference to RCSC with respect to methods of bolt installation, and it's in Chapter 8 of the RCSC specification where we find installation or pretensioning methods covered. So the methods that are included are turn of nut pretensioning, calibrated wrench pretensioning, twist off tension control bolt pretensioning, direct tension indicator pretensioning, and coming in the next edition of the specification is a new method called the combined method, where we combine a method of snug tight using a prescribed torque and then a fully tension condition using an angle of rotation beyond snug tight. There's also a provision for alternative designs, so if you find a fastener that doesn't conform with one of these methods, you're allowed to use it, but there's some prescriptive language that talks about how to make sure you get enough pretension in those alternative bolt designs. So we'll talk about turn of nut pretensioning first, and the basic premise here is that you rotate the nut of the fastener assembly relative to the bolt, and in so doing you stretch the bolt by some amount, and that change in length of the fastener corresponds to a strain, which then corresponds to a stress, which then corresponds to a force. So the basic method is that you snug tighten your bolts, then you put a match mark on the nut relative to the bolt, and then you rotate the nut by an additional angle that will shorten the bolt by a length that is appropriate to get the minimum prescribed tension in that fastener. So the illustration on this slide shows the two match marks in red, and then the nut has been rotated by a prescribed angle in order to provide the minimum pretension. So the image shown here on the left illustrates the match marking. So you can actually see three match marks here, one on the end of the bolt, one on the face of the nut, and one on the face of the base metal. Really the marks on the bolt and the nut are the only ones that are required, though I think a lot of people put the match mark on the base metal as well, so you can tell whether the bolt is being turned. So the ones that are shown on the right have been tightened. You can see that the mark on the nut is been rotated relative to the mark on the end of the bolt. The ones on the left have not yet been tightened. So during an inspection process, an inspector will often come around and look for these marks to make sure that the nuts have been fully tensioned where full pretension is required. Now the angle that the nut needs to be turned relative to the bolt is given in this table. This is table 8.2 out of the RCSC specification, and basically it's a function of the length of the fastener relative to its diameter. So if you have relatively short bolts, you turn the nut 1/3 of a turn relative to the bolt. For a medium length bolt, it's a half of a turn, and for a longer bolt, it's 2/3 of a turn. And then you have other provisions there for the case where the head of the bolt and the nut are being bared against two different surfaces that aren't parallel to each other. So the next method that we'll talk about is calibrated wrench method, and this is most similar to what you might think about if you're used to working on automobiles where you have a prescribed torque that needs to be applied to a nut, say when the installation of a valve cover, or maybe installing a tire where you have to provide, say, 30 foot-pounds of torque to the nut. So this method of installation is based on the idea that there's a relationship between the torque that's applied and the amount of force that's developed in the fastener. And that relationship is shown here, where you have T, the torque applied to the nut or the bolt, is equal to K times the diameter times the force. And K is the nut factor, and it depends mostly on whether there's lubrication between the threads of the bolt and the threads of the nut. So in a case where you have relatively high lubrication, then you end up with a relatively low amount of torque that's required to get a prescribed force in the bolt. If you have dry threads or threads that have a high friction in them, then you end up with a higher nut factor and you require a larger torque in order to get to the same force. So the calibrated wrench method is dependent on a lot of the job site conditions. So you have to make sure that your wrench is calibrated correctly so that if it says you're reaching a given torque, that you're actually getting that same torque. And you need to make sure that the threads of the fastener assembly are in good condition. You can't leave the bolts out to get rusty or dirty or anything like that. So friction between the threads affects the installation process, and even friction on the faces of the nut, the head of the bolt, and the washers also affects the installation method. So this shows an example of bolts that were stored poorly. You have some rust that is developed between the threads of the fastener and on the inside of the nut. So this would probably affect the calibrated wrench method quite a bit, and you might not be able to achieve the minimum specified pretensions with fasteners that look like this. All right, so if we look at the nut factors for a 1-inch diameter A490 bolt, taking that bolt directly out of the keg or out of the can that it was shipped in, we had a nut factor of about 0.179. If we apply some stick wax to it, then that nut factor goes to 0.275. So the premise there is that the bolt was removed from the keg or from the package it was shipped in. The lubrication dried off or evaporated, and then we tried to lubricate it again, but we weren't able to get the same nut factor that we got directly out of the package. And then if you look at the nut factor for rusty fasteners, it goes all the way up to 0.389. So basically you would need between 2 and 3 times as much torque to get the same pretension in the bolts that were rusty compared to the bolts that were coming directly out of the shipping package. All right, that's illustrated here. So with the calibrated wrench method of installation, and in fact with all methods of installation, you have to do some pre-installation verification. And in this case, we show a torque wrench on the left. You can see the dial of that torque wrench down here. And we're calibrating that with respect to the tension in the fastener that is shown here. So this is basically a hydraulic load cell, and as the bolt is tightened, the tension in the fastener is indicated in the dial gauge on top of the Skidmore-Wilhelm torque tension tester. All right, the third method we'll talk about is twist-off or tension control bolt installation. So both the F1852s and the F2280s are twist-off tension control bolts. Also, the F3111s, the 200 KSI bolts, are also, no, I've got that backwards. The F3043s are also tension control bolts, 200 KSI. So these bolts are pre-tensioned using a special wrench. And basically the way that this works is the wrench grabs the spline of the fastener, shown here. This is the spline, and it provides a rotation of the nut relative to the spline of the fastener. And when you end up with a certain torque, then you end up with this bolt shearing off right here in that annular groove that separates the end of the threads from the spline. So these are in effect a torque a torque controlled method because the amount of torque that's applied to the nut is controlled by the shearing strength of the fastener. So you have to use a special wrench, and you have to be cognizant of the thread condition in this one as well. So if you have bolts that have, say, dirty or rusty threads, then you're probably not going to get the minimum specified pretension in the fasteners, even if the splines are twisting off like you would expect. So over here on the right, you can see the wrench. These two fasteners here have been twisted off, so you can see the spline is missing. These three fasteners here have not yet been tightened. This illustrates the method that the wrench uses. So, the wrench has two counter-rotating chucks. The inner chuck here that grips the spline, and then it has the outer chuck here that grips the nut. Okay, TC bolts are often button-head or round-headed fasteners because they can be tightened from one side. You don't have to have a wrench on the head of the fastener to hold the fastener from rotating. And an F436 washer has to be used under the nut when you're pretensioning a TC bolt in order to prevent the nut from gouging into the base material, which would affect the amount of torque that's going into the assembly. TC bolts are susceptible to thread condition, so typically they're shipped as assemblies. You have a bolt, nut, and a washer that are shipped together, as opposed to some hex assemblies where you can get the bolt and the nut and the washer out of separate packages. I think more or less most of the fasteners nowadays are shipped as assemblies, but that's not strictly the case. And then in some cases it may be necessary to pretension a TC bolt without twisting off the spline. Maybe you can't get a wrench, a regular tension control wrench on the bolt, so you can still use a conventional wrench or maybe a torque wrench or something like that to install the bolt. This shows a case, this is actually out of a structure in China, in Shanghai when I was visiting there. And these are tension control bolts. And if you look here, you can see that there are a few of them that haven't been twisted off. And I suspect in this case that they had some interference issues with these bolts coming in on the other plane, and they weren't able to get a wrench on those bolts to twist them off. That doesn't necessarily mean that they haven't been pretensioned, though it's a red flag. The installation crew could possibly have come in and used a hand wrench in order to tighten those fasteners. Okay, the next method of installation that we'll discuss is a direct tension indicating washer, or DTI, direct tension indicator. So these are washers that conform to ASTM F959, and they basically have protrusions or dimples on the face of the washer. And the premise is that as the bolt is tightened, those protrusions will squash out, or they'll squish down or be depressed. And when you're no longer able to fit a feeler gauge in between those dimples like this, then the bolt is said to be tight enough so that minimum pretension is achieved. Now these washers are calibrated to the specific bolt you're using. You can see this one here says A325 on it, so it has a sufficient number of dimples that it will achieve minimum pretension for an A325 fastener. Excuse me, but you couldn't use that with an A490, for example. So you have to look at the face of the washer to make sure you're using the appropriate washer for the grade of fastener that's being installed. So the location of the DTI washer with respect to the turned element is critical when you install assemblies using the DTI method of installation. And it's illustrated here in words, but basically the idea is that you don't want to have the turned element of the assembly directly adjacent to the protrusions on the direct tension indicator. If you're turning a nut against those protrusions, then instead of squishing them down or compressing the protrusions, you might actually grind them off, and you might not achieve a minimum pretension even though you have a sufficient number of refusals of the feeler gauge. So yeah. This slide illustrates the correct location for the direct tension indicator given different configurations of installation. So case A, the DTI is under the bolt head and the nut is turned, so that's sufficient. In case B, the DTI is under the nut with the nut being turned. So in this case, you have to have a second hardened washer so that the nut isn't bearing directly on the protrusions and then being turned against them. Case C shows a DTI under the bolt head where the head of the bolt is being turned. So in that case, you would need a second washer, a 436 washer there, so that the head of the bolt isn't being turned directly against the protrusions. And then finally, you can see in the case on the right, you have a DTI under the nut. In this case, the head of the bolt is turned, so having the protrusions bear directly against the nut is acceptable. Note in all four of these cases that the protrusions are not bearing against the base metal. The protrusions are bearing against the hardened material of either the nut, the head of the bolt, or another F436 washer. Okay, there's a variant of the DTI washers that are called squirters, and the idea here is that if you look at the back side of the washer, there is an indentation behind each of the protrusions, and it can be somewhat tedious to have to check the feeler gauge of a regular DTI all the time, so they come around with the idea of the squirter is that you fill that indentation with some type of a paint, or I think it's like a plastic silicone, and when the protrusions are squashed out or depressed, then that paint squirts out the side of the washer, and that's an indication that you can use your feeler gauge at that point to check see if all the dimples are depressed enough that minimum pretension is achieved. So these images show what it looks like when that paint or that silicone actually squirts out. So the fact that the paint has squirted out isn't an indication that the bolt is tight. It's just an indication that you can then use your feeler gauge to check to make sure that that gap is small enough that the bolt has actually been tightened. So the last method that we'll talk about is the combined method of installation, and this isn't in the 2014 edition of the RCSC specification, but will be coming into the 2022 edition of the spec. So with the combined method, you achieve a given snug tight condition using a prescribed torque. So you have a prescribed torque that's in the RCSC specifications in the 2022 edition, and you apply that torque to the bolt first to get you to a snug tight condition, and then you use an angle beyond snug tight in order to achieve fully tensioned. So the combined method using the torque and angle 144 bolts is a little bit different in that these fasteners have a fixed spline attached to them as opposed to the detachable spline that a tension control or a twist off bolt would have. So you can see the two different types of bolts shown here at the bottom, and what's missing from the torque and angle bolt is the groove between the ends of the threads and the spline that's attached to the end. So with a torque and angle installation, you use a special wrench that both is able to measure torque and to measure angle, and you basically put it in torque mode to get to the snug tight condition, and then you switch the wrench from torque mode to angle mode, and you achieve the final tensioning. But in the end, the spline of the group 144 bolt does not twist off from the end of the bolt. Okay, alternative design fasteners are permitted as well. I won't go into too much detail about these, but basically you have to come up with an installation method that assures the engineer of record that these bolts are going to achieve the pretension that is needed for them to function properly in pretensioned or slip critical joints. Okay, here's some more about the installation. It talks about the type of installation, pre-installation verification, the alignment of bolt holes, systematic assembly of the joints, etc., etc. And these all have to be approved by the engineer of record before these alternative design fasteners can be used. Okay, here's an example of an alternative design fastener. These are Huck bolts, and these have been on the market for quite a while. They're similar in some respects to a rivet as opposed to a bolt, in that the grooves that are around this are actually annular instead of helical. So the special wrench is used to provide a pretension to the bolt, and then the outer chuck that's shown in green on this slide is actually deformed around those annular grooves to keep pretension in the fastener after the tightening device is removed. Okay, here's another example of alternative design fasteners. These are called blind bolts, and they're so called because you can't often see the inside face of the fasteners after installation. So these are often used in connections to HSS members or tube members where it's not feasible or not possible to actually get a nut on the inside of the tube. So in this case, it has some deformable parts that would supposedly allow the bolt to achieve its minimum pretension or achieve its tensile capacity without pulling out of that hole. Okay, here's another example of, I guess they're called Avdel blind bolts, and similar to the Huck bolt, except in this case there's a deformable collar that goes around the bolt between the surface of the bolt and the inside surface of the hole. But then you have that deformable collar that is shown here that actually is compressed somewhat like a rivet to provide the grip on the material. Regardless of which installation method is used, pre-installation verification before the bolts are installed is required. This PIV testing, pre-installation verification testing, is there to provide a means of ensuring that bolting assemblies that are non-conforming are identified before they're put into the structure. Maybe you have bolts that don't have enough lubricant on the threads or whatever, and they won't meet minimum required pretensions. Or maybe there's a wrench or a tool that has not been certified. Maybe somebody dropped a torque wrench, for example, and it no longer reads correctly. It's also there to make sure that bolting crews know the proper installation method. So it kind of gives them a dress rehearsal for installing the bolts using the appropriate installation method. So we looked at the Skidmore Wilhelm torque tension tester under calibrated wrench, but it's used for all of the different installation methods during pre-installation verification testing. Basically, like we said earlier, it's a donut-shaped load cell. There's a hydraulic oil in it. The bolt is installed from the rear. The nut is installed on the front, and then you tighten the bolt using the method indicated and make sure that the minimum required pretension is achieved. So pre-installation verification testing is critical for these different reasons: to make sure the bolting assembly is adequate, including lubrication, etc. To make sure that you're using the proper method. Several different methods of installation. We want to make sure that it's being conducted properly. To make sure that the tools are properly calibrated, and to make sure that we have other suitable equipment. It also provides an arbitration torque in the eventuality that there's some sort of arbitration at based on the bolt installation. PIV testing is supposed to be conducted on the site, the construction site. It's supposed to be conducted prior to placing any of the bolting assemblies in the work. It's supposed to be conducted using bolting assemblies that are basically the same ones that are going to be used on the job site. And in fact, if you go to a different size or even a different lot of fasteners, you're supposed to perform PIV testing for each one of those sizes, each one of those manufacturer lots. And you're supposed to use a sample of not fewer than 3 of the bolting assemblies to make sure that it works all 3 times. Installation inspection is required on most job sites, and this is in addition to what the erector might have in place. Tests and inspections are often specified by the engineer of record and might be specified in local building codes as well. Snug tightened joints often have to have visual inspection to make sure that there's firm contact between the plies of the joint and to make sure that the washers are used properly. Pretension joints often require pre-installation verification and observation of the installation of the bolts in the finished joint. And finally, slip critical joints sometimes require, above the installation inspection for pretension joints, require that fang surfaces be inspected prior to the joint being assembled. Generally, an inspector would look for match marks for turn of nut installation. They would look to see if the splines of TC bolts or twist-off bolts have all been snapped off. Or they might want to observe a bolting crew actually installing bolts using the combined method or maybe the calibrated wrench method. If DTIs are used, they'll go around and look to make sure that all of the protrusions have been depressed and that the feeler gauges aren't able to be inserted in between those protrusions. Bear in mind, though, in some cases, if you use twist-off bolts, that it might not be possible to fit a wrench on to snap off the splines. So in those cases, you can use alternative methods to install those twist-off bolts, even if there are splines on the ends. So the term stick out sometimes comes up when you talk about installation inspection for fasteners. Stick out is basically the amount of threads that extend beyond the face of the nut after the bolt has been snug tightened or fully tensioned. And some inspectors or some engineers, erectors, have the misconception that you have to have the thread sticking out beyond the face of the nut. And that's not true. You can actually, as long as you have a zero stick out, then everything is fine. In other words, as long as the nut and the end of the bolt are at least flush, then the fastener should perform adequately. You don't need to have a positive stick out. A zero stick out is acceptable. So the last thing that we'll talk about in this presentation is the storage of components. Fastener components have to be stored in such a way that they're protected from dirt and moisture. Only fasteners that are anticipated to be installed in a given work shift are permitted to be taken out of that protective storage. And protective storage is defined as a continuous protection of the fastener from the elements in closed containers or in a protected shelter. Any unused fasteners must be promptly returned to the protected storage. So this slide shows some proper storage of bolting assemblies. You can see these kegs here in the foreground. These here are yellow and green with red tops, but there's also some kegs back here in the background that are black. And those are sealed so that water can't get in, you can't get humidity into them, etc. This pallet of boxes back here is presumably some bolts as well. And the cardboard itself doesn't provide adequate protection, but inside of those boxes are some heavy thickness plastic bags. And those plastic bags are usually sealed shut either with a Ziploc top or they have some type of a twist tie on them. And then down here in the lower right, what you can see is that each one of the containers is identified with the manufacturer's lot number, the size of the bolt, the grade of the bolt, etc., etc. That way that you have proper traceability and so that the bolting crew can install the proper bolts in the proper joints. This slide shows a close-up of one of the tags you would often find on a keg of bolts. In this case, we're dealing with A325 TC bolts. So the TC stands for tension control or twist off. They're 3/4 inch diameter, presumably 2 inches long, and there's 148 pieces in that particular keg. And it also gives the manufacturer's lot number so that you have traceability back to the testing that was done at the manufacturer, both with respect to strength and with respect to torque capacity for installation. This is an example of improper storage. I won't identify the job site that this came from, but it was a bridge job actually. So you go onto the job site and apparently the bolting crew left this bucket of bolts in their staging area the night before, hopefully the night before, it could have been the week before. And it rained that night, so there was some moisture that built up on those bolts. In fact, at the bottom of the container, they might actually be sitting in some standing water. And since these bolts don't have any protective coating on them, aside from a little bit of oil, it doesn't take a whole lot of moisture for the threads to start to get rusty. In fact, the bolts that are in the container on the left, you can see some surface rust that has started to form on the fastener. Now that rust doesn't necessarily compromise the strength of the bolt, but it could easily compromise the minimum pretension that's achieved if you're using a torque-based installation method. Okay, lubrication to these fasteners is vital, particularly for methods that are torque-based, like the calibrated wrench method or the twist-off tension control bolt method of installation. The lubrication that's applied is often water-soluble, and this oil is easily washed off when they're exposed to the rain or the moisture. But there's a provision in there that says that twist-off bolts F1852 or F2280 shall not be re-lubricated by the manufacturer. You can actually get into trouble if you were to take a can of WD-40 or something like that and spray that on those bolts. You can end up with installation problems where maybe the bolt would start to strip off or something like that. And that shouldn't happen under normal conditions, but when you start playing around with re-lubrication, then that can be a problem. And then here are some issues associated with the storage of galvanized bolts. Galvanized bolts are a little bit different in that sometimes you have over tapping of the nut so that you can allow more clearance between the threads of the nut and the threads of the bolt for the thickness of the galvanized coating. So in those cases you can get poor thread fit if you end up mismatching components from different assemblies. And it says that lubrication on galvanized fasteners is generally more durable than on black bolts, but protective storage is still recommended. And as it stands right now, A490 bolts or 150 KSI bolts are not allowed to be galvanized. Overseas they are. In Europe you can galvanize the equivalent of A490s or F2280s, but in the United States right now you're not allowed to have galvanizing. Instead they have different coatings like a dacrymet coating that provides some weather protection for the bolts that's similar to what you would get from galvanizing. Okay, so that brings us to the end of this presentation. At this point, you should have a good idea of which grades of fasteners are available and the 5 different methods of installation you would see in most common job sites. You could probably move on at this point to start looking at bolted connection fundamentals and then maybe move on to welding fundamentals and welding connection fundamentals. Thanks a lot.